Welcome to the autoionization of water. As the title suggests, water is capable of ionizing with itself to produce hydronium ions and hydroxide ions, as seen by the equation shown. Through very careful experimentation with pure water, it has been found that at 25 degrees Celsius, about only 1 out of 10 million molecules autoionize. Recall from the last section on the Bronsted-Lowry theory, acids are proton donors and bases are proton acceptors. I want you to look now at the products in this equation. Particularly, let's look at the original water and the hydronium ion that it produced. If this water was converted to hydronium, you must now ask yourself, did it accept a proton or did it donate a proton to become H3O positive? It should be easily seen that water here must have accepted another proton to gain a hydrogen and a positive charge. Therefore, the first water is acting as a base. If we were to look at the second water molecule and the fact that this became OH-, it should be confirmed that the second water is in fact acting as an acid since it becomes OH-, meaning it lost a proton and a positive charge. This also confirms from the last lesson that water is in fact amphoteric. It can act as an acid or a base. Also recall from the kinetics and equilibrium unit how to write out equilibrium expressions. Remember, for an equilibrium expression, it is equal to products divided by reactants raised to the power of their coefficients. Also recall that in an equilibrium expression, solids and liquids are not included since they do not have a concentration. Remembering this, you can see that in the autoionization of water, we will not include the initial water molecule or the second water molecule because they are in fact liquids. Since we're talking about the autoionization of water, and the equation for the autoionization of water is always the same, instead of denoting the equilibrium expression as KEQ or KC, like we saw in the equilibrium chapter, we're now going to denote this as KW, where the W stands for water. Since liquids are not included in an equilibrium expression, the autoionization of water can be expressed as KW is equal to H3O positive times OH-. Please note that in Chemistry 3202, this expression will not be given to you, and you're required to memorize both the equation here as well as the equilibrium expression. Since the equilibrium constant for the self-autoionization of water is always equal to H3O positive and OH-, Kw is a constant, and it is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. This constant is given to you on the back of your periodic table in Chemistry 3202. Since Kw is always equal to H3O positive times OH-, and at 25 degrees Celsius this is equal to 1 times 10 to the negative 14, we can very easily discover the concentration of H3O positive and OH- at 25 degrees. At 25 degrees Celsius, water is a neutral compound. If water is a neutral compound, that would mean we do not have more acid or more base. We would have equal amounts. If Kw is equal to H3O positive times OH-, and pure water is neutral, then there's no more acid or no more base than the other. We have equal amounts. Therefore, we can represent this as 1 times 10 to the negative 14 is equal to x times x, since we have to have equal amounts. If we want to obtain the value of only 1x, hopefully you can see we can take the square root of both sides. When we take the square root of both sides, H3O positive is equal to OH minus, which is equal to 1 times 10 to the negative 7. This is the concentration of both hydronium and hydroxide for pure water at 25 degrees Celsius. If we're in a situation where we increase H3O positive, then OH minus must decrease, since the product of the two must always be 1 times 10 to the negative 14. This is a constant number that does not change. Likewise, if we decrease OH minus, then H3O positive must decrease. Oh, that is a typo. So we'll change that in the notes, please. That must increase. Again, since the product of the two will always be the same. A popular multiple choice question that pops up is if we're in acidic or basic conditions. Remembering that water is amphoteric and can act as an acid or act as a base, there are times when we have acidic water or basic water. This is a concept that we're going to explore a little more in IB chemistry with regards to hard water versus soft water. If water is in fact acting as an acid, then we have more acidic components, or H3O positive, than we have base components, or OH minus. If there is more hydronium present, then the concentration of hydronium will be greater than 1 times 10 to the negative 7, since it is no longer neutral. And if it is acting as an acid, then the base component, OH minus, will be less than 1 times 10 to the negative 7. The reverse is true for basic conditions. The diagram at the top of page 2 is a great pictorial representation of what we've just been talking about. If water is in fact acidic, then there is more hydronium than hydroxide, therefore the larger font. If water is neutral, then we have the same amount of hydroxide and hydronium, and therefore they're written in the same font. And if it's a basic solution, there's a lot more hydroxide than hydronium, which is why it's written larger. This may be an easier way for you to remember this concept. Let us now work through some example questions. At this point in the video, you may want to pause and try these on your own first. If you feel comfortable with the content, you can then move on to the worksheet. I would strongly encourage that you write down the answers to these examples while you work through the video. You may need to pause and repeat just to make sure that you're understanding the concepts. In the first example, we have been told that hydronium concentration is 1 times 10 to the negative 5, and we've been asked if it is acidic, basic, or neutral. Well, if H3O positive is equal to 1 times 10 to the negative 5, we need to compare this against how much it is when it is neutral. 1 times 10 to the negative 7. You need to now ask yourself, is 1 times 10 to the negative 5 greater than, less than, or equal to 1 times 10 to the negative 7? And hopefully you can see that 1 times 10 to the negative 5 is greater than 1 times 10 to the negative 7. Since it is greater than, and we're talking about hydronium, then this solution is acidic. The next part of this example asks us to discover the concentration of hydroxide. When you're asked to find the concentration of hydroxide and you know hydronium, or you're asked for hydronium and you know hydroxide, then we can use the expression Kw, since that is a constant, is equal to H3O positive times OH minus. Again, Kw is a constant, 1 times 10 to the negative 14. We know that hydronium is 1 times 10 to the negative 5, so we can figure out hydroxide. In order for us to get the concentration of hydroxide, we need to divide both sides by 1 times 10 to the negative 5. If you were in Chemistry 3202 right now, and this was a multiple choice question, you can very easily plug this in on your calculator to get an answer. However, this is the type of multiple choice question you can see in IB, so make sure you review your rules for the exponents, since they have the same base. And in this case, the answer is 1 times 10 to the negative 9. As well, since we're solving for the concentration, we must include our units of moles per liter. The next example is slightly more tricky. We have a solution of barium hydroxide where we have been told that the concentration is 0.1 molar, and we've been asked to find both hydroxide and hydronium concentration. The first question you must ask yourself is barium hydroxide. Is this molecular or ionic? Hopefully you recall from Science 1206 that an ionic compound is anything that contains a metal, which is barium, and nonmetals, oxygen and hydrogen. Then you have to ask yourself, what does ionic compounds do in solution? And you should remember from Chemistry 2202 that an ionic compound, let's try that out again. An ionic compound such as barium hydroxide will dissociate out in solution to give us its two component ions, Ba2 positive and 2 OH minus. Since ionic compounds do dissociate out into solution, if I have a 0.1 molar solution of barium hydroxide, I can very quickly find the concentration of OH minus using our mole ratio, as we did in the solutions chapter of Chemistry 2202. Recall from 2202 that the mole ratio requires you to multiply by the coefficient of the required over the coefficient of the given. In this question, we are required to find the concentration of OH minus. It has a coefficient of 2. We were given the concentration of barium hydroxide. This has a coefficient of 1. Therefore, the concentration of hydroxide is 0.200 molar. And make sure you label that so that your teacher or the person who's correcting your exam realizes what that is the concentration of. Now we're in a situation like the last example, where we've been asked to find the hydronium ion concentration and we have the hydroxide ion concentration. Therefore, we can use Kw. Remember that this formula is not given to you, and it is something that, with enough practice, you should easily memorize. Kw is always 1 times 10 to the negative 14. In this case, we're looking for H3O positive, and we now know that hydroxide is 0.2 molar. Again, we can find hydronium by dividing both sides by 0.2. And then that crosses out. Therefore, H3O positive is equal to, and this is my disclaimer at this point. If you are watching this video and simply writing down what I am in under each of the examples, I strongly encourage that you now take out your calculator and make sure you get the same answer as I do. You should get an answer for hydronium to be 5.00, keeping the right number of significant figures, times 10 to the negative 14 molar. This should also make sense logistically. Remember that we started with a solution of barium hydroxide. Since barium hydroxide contains the hydroxide ion, we can very easily identify this as being a strong base. Since this is a strong base, we would expect that the hydroxide ion concentration would be greater than 1 times 10 to the negative 7, and the hydronium ion concentration would be less than 1 times 10 to the negative 7. Finally, in our last example, we have a solution of HBr, or hydrobromic acid. I ask you now, hydrobromic acid, is this a strong acid or a weak acid? If you're struggling with remembering your 6 strong acids, at this point you can also look at your acids and bases strengths table, remembering that the top 6 are the 6 strong acids. When doing so, you should see that HBr is in fact a strong acid. Recall that strong acids ionize out 100%, meaning they break apart into their component ions and are 100% converted to the products. So I can take HBr and break it up into H positive and Br negative. Since the question is asking us to find the concentration of hydroxide and hydronium, there are 2 different ways in which we can approach this question. A lot of you are probably asking at this point, well, how can I find hydronium ion concentration if I have just H positive? Well, recall from the modified Arrhenius theory that H3O positive is equal to H positive. It was simply made up to replace H positive from the original Arrhenius theory. So you can just continue on with the question thinking of H positive as H3O positive. If this is confusing for you, you can also take HBr, which we know is the acid, and react it with a water molecule, knowing that's in aqueous solution, to get H3O positive and Br negative. Either way would suffice. Now that we know that we have a HBr concentration of 1.50 molar, we can find the H positive concentration or H3O positive concentration, whichever way you decided to proceed, by multiplying it by the mole ratio. The required is H3O positive, and that has a coefficient of 1, and the given is hydrobromic acid, which also has a coefficient of 1, meaning that the hydronium or H positive ion concentration is the same. This should make sense, seeing as we have identified this as being a strong acid, and it should make sense that the concentration comes out to be greater than 1 times 10 to the negative 7. And, like the last 2 examples, once we know H3O positive, it is easy for us to find OH minus by using the Kw equation. Kw is 1 times 10 to the negative 14. We know that H3O positive is 1.5, therefore it's very easy for us to find OH minus. We simply divide both sides by 1.50. That cancels out, and therefore we get a final answer. Plug it in on your calculator. 1 times 10 to the negative 14 divided by 1.5 to 3 significant figures is 6.67 times 10 to the negative 15, and as always, do not forget your units. At this point now, you can go ahead and work on the worksheet. Good luck!